of computer science and electrical and computer engineering. He's also a CFAR Canada AI chair and a founding member of the Vector Institute. And before that, he was a research fellow at the University of Cambridge. So Dan has made very nice contributions to packed Bayesian analysis, non-parametric Bayesian modeling, probabilistic programming, sampling, and other fields. And of course, Dan is known for naming a stochastic process after a French painter, Mondrian. And of course, I invite all of you to follow up. And I'm already thinking of a Kazimir Malevich follow-up, Black Square. So I'm very happy to have Dan here. And let me also say that Blair Bilodeau, is that the right pronunciation? Probably not. He's a third-year PhD candidate in the Department of Statistical Sciences at the University of Toronto, and his research is on combining techniques from statistics and computer science to obtain theoretical performance guarantees for decision-making. So please take it away.
Thank you for that nice introduction and for inviting us. So I'll start, and Blair will take over shortly after that. So let me start with some background, and in particular, motivating example. So that motivating example is going to be trading stocks. So you need to invest your money in some stock portfolio, and you have access to several market experts who are willing to give you advice. So you could say interview them in advance and pick one and stick with them the whole time. But maybe you can also observe how they're performing over time and aim to swap who you're working with throughout in order to, say, do better than you would have done had you not tried to adapt. Now, at the end of the day, you're going to regret, of course, not having had omniscience and picked the best expert in advance without knowing how the future was going to look. Now, we have to decide somehow some way to trade. And usually it's going to start with making some kind of assumptions. And then once we've made assumptions or decided how we're going to think about our performance, then we can try to derive an optimal response with regards to those assumptions we've made. So one classical set of assumptions we can make would maybe be, say, adopt the kind of underlying assumptions in, say, Black-Scholes. So we assume the stock prices are following a geometric Brownian motion. So the log stock prices have independent increments. So this would be an assumption. You could then derive an optimal response with respect to it. Now, we've seen recently with, say, the insanity around GameStop there, that the market can sometimes be driven by non-stochastic forces. So if you're going to leave the comforting world of this nice kind of nice stochastic assumption and start worrying about adversaries who are out to get you, then where do you stop? You can come to another sort of stylized assumption other than, say, geometric Brownian motion, or you could go all the way to this, maybe the next most natural resting place, and do an adversarial analysis where you think at every single moment people are out to get you. Now, maybe I think in most situations, just assuming that the data is adversarially chosen for you is a bit too pessimistic. But at the same time, how do you think about how the data might be merely a departure from I.I.D-ness? In what sense might it be a benign one? And how might you quantify that? You might hope that the influences of the non-stochastic forces in the market are small and not going to affect you. But then this just sort of raises the question of what it means to be small. So we'd like to work out some way to maximize our profit without knowing in advance what is actually driving the market. And this is a stock market example, but I think this sort of question is at the heart of a lot of statistical analysis. How do we decide what assumptions to make? And whenever you write down assumptions, you can almost always kind of imagine that they're not actually going to hold. So the framework we're going to be pursuing this question is the framework of sequential prediction with expert advice. There are some world experts in the audience, but I'm going to introduce the framework nonetheless. So I'll start with sequential prediction. So it unfolds in rounds. At each round, we're going to issue a prediction y hat, which can be based upon historical data we've seen up until that time. Then after our prediction has been issued, we make an observation of an outcome y of t, and we incur some loss, which depends on our prediction and on the observation. So these observations, the outcomes might depend on our predictions. They might depend on the history, or we could be in an I.I.D situation where the outcomes are being drawn independently and identically each round. So the framework of sequential prediction with expert advice, we get another piece of information at the start of each round, in particular a vector of predictions from our experts. And we can use these predictions in the formulation of our own prediction. And the observations, the outcomes might be dependent. There might be collusion between the experts and the way that the world unfolds. So just to put this in pictures, so this is the information that's kind of flowing through this game. On each round, we're making predictions that are based on the experts, and there can be some kind of hidden data which is driving also the losses in the expert predictions. So this is our history, say round one. On each round, we get additional expert predictions, and our predictions can depend on that past history and on these predictions being given to us, and so can the data. And so our history kind of grows, and we can depend on more and more and more. So now that you understand roughly the dynamics of this game, we're making predictions each round. There's some kind of history, and we're given this expert predictions also to potentially base our predictions on. I want to discuss the question of how we measure our performance. So we're going to measure our performance relative to this class of N experts. So we're going to be being given expert advice, but then we're also going to measure our performance against those same experts. And we're going to do so by looking at the excess cumulative loss we're incurring above and beyond that of the best expert, at least in the single best expert in hindsight. So as a formula, our regret after capital T rounds is going to be the sum over those rounds of our losses, subtracting off the least loss incurred by a single best expert. So in a worst case setting, we talk about this prediction problem being online learnable if the player can guarantee that their regret is growing sublinearly, meaning that their average per round regret is vanishing. Now, in our setting, we're going to be interested in going beyond this worst case analysis. So there's at least going to be multiple sources of randomness we're contending with here. So it's typical to use randomization when you're producing your predictions here to deal with adversaries. But we're also going to be potentially, if the data are I.I.D, then we're going to have to also be contending with the randomness in the experts' predictions and maybe also the data generating mechanism. And critically, this expectation here may be quite complicated. It's not necessarily going to be an I.I.D measure. It could be, we could be facing an adversarial situation where there's collusion behind the scenes, and there's definitely no independence across rounds. So let me talk about kind of optimality in these two extremes, in the stochastic setting and in the adversarial setting. So in the stochastic setting, we have the framework of stochastic with a gap. So in this setting, the expert predictions and the losses we're incurring, these are the data in some sense, are assumed to be independent across rounds and identically distributed. And we're also going to assume that there is a single best expert, and we're going to use capital delta to denote the difference in mean loss between the single best expert and all the other experts. So there's at least this gap of delta there. And in this setting, we know by earlier work that there is an explicit algorithm, a very simple one, that achieves the minimax regret. And that minimax regret is even uniformly bounded in T, so it doesn't grow unbounded in T. And it is depends on these two parameters, namely the number of experts and this gap between the best expert and the next best of delta as log n over delta. So this is a minimax regret. Now, at the other end of the extreme is the adversarial setting, where our strategy is known, and the experts and the observations can kind of be chosen together to maximize their regret. So in this setting, classical results tell us that again, there's an explicit algorithm that achieves a minimax regret, which grows as root T log n. And so comparing these two, you see a massive gap between these two. And it's an interesting question to ask, well, if I don't know which of these two situations I'm in, then is there a way to behave such that when I happen to be in the nice situation, I can somehow recognize so and achieve the minimax regret of that nice situation? And if I happen to be in an adversarial situation, I can somehow be robust and still not attain much worse than the minimax regret there too. So this is a question that's been recently answered for a well-known algorithm called Hedge in work by Mortada and Gaifa. So just here again, I'm copying the minimax regret in these two scenarios. And here is just a picture of the performance of Hedge, which is indeed as they show in their work, is indeed incurring the right regret in both these scenarios. So in the blue data, we're simulating an adversarial sequence of data, and Hedge is indeed incurring square root of t regret, and its dependence on n is correct as well. And I can also feed that exact same algorithm without knowledge, and that algorithm has no knowledge with these two situations it is. But if I feed it an I.I.D sequence, then you see at some point its regret plateaus, as you would expect if it was achieving the minimax regret. All right, now this is extremely interesting because we can be in one of these two situations, not knowing which. We can have a single algorithm that performs well in both. However, real data is not going to be stochastic. That's too optimistic, right? I.I.D is a kind of extremely useful assumption. You can design things that are I.I.D and they work well, but like the theorem doesn't tell you that it's going to work well in small perturbations of I.I.D-ness, whatever that means. At the same time, the real data is unlikely to be adversarial. That's far too pessimistic. And so what we'd really like is to work somehow with a spectrum of situations and be minimax optimal no matter where we land. And so we're going to adopt this and build on the framework introduced in work by Sasha and Karthik and Ambuj in 2011. And in this framework, what the starting point is to fix a kind of set of allowable distributions, a neighborhood of distributions. And then at each round, say, rather than say the rounds being always the same, which is stochastic, or always kind of being able to be chosen arbitrarily, we're going to force like the data that appears at a particular round to fall in this neighborhood. So here's a picture. Okay, yeah, having some slide issues. 1 second. Okay, so here's a picture of that. So in the stochastic setting, we see that these triangles are depictions of the probability space of all probability measures. So this is kind of probability simplex. In the stochastic setting, every single round we're getting data from the same distribution. In the adversarial situation, at every single round, the adversary is unconstrained. They can make an arbitrary choice based upon the data that has been seen before and even the predictions we're making. So in the setting we're going to now consider this neighborhood following this framework introduced by Racklin, Shadar, and Tawari, but we're going to allow non-oblivious adversaries here, so that they're allowed to make an arbitrary choice, but within this constraint set, and that choice can depend on our predictions. Right. And the idea basically, if this if this green region is very, very like concentrated around a distribution, that's like sort of a notion of like a slight variation of an I.I.D setting. So what we'd like prediction algorithms that are robust to say the range of settings of the range of data generating mechanisms we might like. So we'd like to potentially be dealing with an adversary who's constrained in this way and still with a single algorithm behave in a minimax optimal way, no matter what situation underlies the data. So so what we want is a notion of adaptive minimax optimality, meaning that we want to achieve the minimax optimal performance in each setting, but without knowledge of what that true setting is. And so, to formalize this, how this will work is we have some range of abstract settings, lambda. Think about this lambda specifying like some properties of that constraint set, and then given the particular setting that's in that constraint set, say some particular setting theta is actually happening, there is going to be some minimax regret for that setting. And then what we want to happen is we want to have a single algorithm whose regret in a particular situation theta is no more than a constant multiplicative factor off of the actual minimax regret in the actual situation. But we want this bound to hold uniformly in the situation theta, so that which kind of encodes the idea that we don't know a priori which situation we're in. So we're going to have we're going to perform as well as if we knew the situation that we were in. All right, so that's the situation. I'll now hand it over to Blair. Blair, I presume you're ready.
Yeah, thanks, Dan. Let me just share my screen now. Okay, you can share see my screen.
Can I ask a quick question?
Yeah, for sure.
is the distribution allowed to change from step to step as t goes to 1 to t, or you assume that there is one correct distribution and there is a certain set about
so the kind of ball that Dan was describing, that little like green bubble, that can't change with time, but the idea is the adversary gets to pick a distribution, a different distribution within that ball at each time. So the actual distribution can change over time. Yes. So now that kind of Dan has described the setting that we're working in and what it means to do well in this setting, let me give an overview of kind of what are the results that we're able to state within this setting and notion of performance. So the first thing that we're going to show is that hedge is actually suboptimal in between these two endpoints. So it's known to be optimal at the stochastic and adversarial endpoints, but it's suboptimal everywhere in between. This was surprising. We actually set out in this work hoping to show that hedge was optimal everywhere. That's kind of a natural thing to expect. But it turns out if you don't have knowledge of which setting you're going to be in advance, so we call this oracle knowledge, without that, then hedge is not simultaneously minimax optimal at all of the settings in between the stochastic with a gap and adversarial case. So what we do is we provide a new algorithm that does achieve this minimax rate in all of these settings along the spectrum, and it does so without having to know in advance which setting it's going to be in. So by definition, that means that this algorithm is adaptively minimax optimal, and we call this algorithm Medicare for reasons that will become clearer a little bit later. But first, I'm going to kind of dive into a little more detail of what this positive result looks like. So what our bound for Medicare is going to look like. A little bit of intuition to motivate what this result looks like is in the adversarial case, recall that we said the minimax optimal regret is known to be square root t log n, where n here is the total number of experts. And imagine that someone told you in advance that some small subset of these experts would only be the best, so some amount n0. Then you could just run your kind of adversarial algorithm only on this small subset and kind of ignore all of the other ones outside of that. And you would hope to get square root t log n0 regret. So you have a dependence on just this number of the small subset instead of the total number of experts you might have to be competing against. And so we would hope that we can achieve this type of regret without having to actually be told in advance what n0 looks like. Similarly, we could be told that some expert is going to be better than the rest, and that we mean here an expectation, and it's going to be better by at least some small amount, some delta 0 here. This is almost the stochastic with a gap case. I say almost because we don't even need to require this to be I.I.D. The distributions could still be changing over time as long as the same expert is kind of best in expectation and it's best by some small amount delta at least. We would hope to get regret that looks like the stochastic with the gap case, so constant in the number of rounds, and of this form log n over delta 0, where delta 0 is the gap here. And it turns out this is exactly the case. So we prove that the adaptively minimax optimal rate of regret is in the case where there is only kind of one good expert, this n0 is equal to 1, you get constant in t regret, so we get this log n over delta 0. And if you have more than one expert, you have regret depending on t, in this way square root t log n0, but this can be much better than square root t log n, which is what you have to incur if you're competing against all of the experts, so all n of them. And Medicare actually achieves this rate of regret, and it does so without having to know in advance what n0 is, or delta 0 is, or anything about which setting it's in. You can just run the algorithm, and it will get this right rate of regret. So by definition, that means that it's adaptively minimax optimal. So now I'm going to describe a little bit more about what the hedge algorithm is so that I can talk about what kind of performance it gets and also how we're going to modify it to obtain an actually adaptively minimax optimal algorithm. So a bit of bookkeeping. We're only considering finite expert classes here, so where that n is finite, and we also need bounded losses. So without loss of generality, let's suppose that our losses are bounded in 0, 1. We're also going to consider proper algorithms in this work. And so what a proper algorithm means is that rather than making kind of an arbitrary prediction from your prediction space at each round, you pick one of these finitely many experts and you emulate them at that round. By emulate, we just mean you play exactly the prediction that that expert has played. And so one way to view this is that the algorithm is going to assign a distribution to these experts, which we denote by this weight vector W, and then randomly sample an expert according to that distribution and emulate whichever expert it's sampled. So this might seem a bit restrictive, but it turns out that hedge is a proper algorithm. The algorithm we define is proper, and also our lower bounds hold for both proper and improper algorithms. So basically this setting of prediction with expert advice, where you have finitely many experts and bounded losses, is kind of resolved by just thinking about proper algorithms. So now let me describe hedge, which I'm going to do by describing how it chooses what this weight distribution W is. So it's going to be parameterized by a learning rate schedule, so just a sequence of learning rates it's going to use at each round. And let's initialize the weights to a uniform over the experts. A bit of notation, the loss of the ith expert at round t is this little l of I, and then the cumulative loss that that expert has incurred over the first t rounds is a capital L. So then the weight update rule for hedge is this exponential update rule here. So we have the weights are proportional to, where proportional just hides a finite renormalization because we only have finitely many experts. So when this loss gets larger, this L of I, then that means that the ith expert incurred more loss. And so we want to put less weight on this expert. Because we think that it's kind of doing less well. Similarly, if that loss is small, we want to put more weight on that expert. We want to be more likely to emulate it. And the amount that we kind of upweight and downweight is going to be decided by, or encoded by the fact that we're using an exponential update rule here, and also this learning rate eta.
So I guess the difference with the standard exponential weight update is just that you select one expert as opposed to averaging.
So we can view this as we're looking at expected regret. And so that's kind of equivalent to basically sampling an expert and playing that, or looking at the inner product of the weights and the losses at the same time. So they're equivalent. We're just kind of motivating this as though you can think of it as actually sampling an expert and playing that one. But since we take expectation, it's the same. So recalling what this kind of update rule is here, I'm now going to define an equivalent way to state these updates for hedge, which is going to be the variational formulation. So the first thing I want you to realize is that if we set this learning rate to just be constant for a moment, so it's not depending on time, then this looks like a Bayes rule update for an expert valued parameter. So kind of choosing a Bayesian distribution over the n experts that we have, where we're taking a flat prior, so a uniform prior over the experts, and our likelihood is this exponential term, this e to the negative eta times the likelihood. And so an equivalent way that I can write these hedge update rules, so we have kind of an explicit form of this in the exponential update, but I could also write the weights as solving an optimization problem. And so this optimization problem is going to be argmin over weights in the simplex, so actual probability distributions over the experts of kind of two terms in the objective. So the first of these is the expected loss of the experts under this weight distribution. So this is a linear term. And if we just had this term, then we would put all of our weight on the expert that has done best so far, because we would just, that would solve this linear objective. But we don't want to do that because that's kind of overfitting to our data. And in particular, we're allowing our data to be kind of ranging between stochastic and adversarial. So you can imagine that could be a bad choice to kind of just follow whatever's been best so far. So we're going to regularize by the Shannon entropy of the weights. So the Shannon entropy just measures kind of how dispersed the weights are to move away from having a point mass distribution and look a bit more like a uniform. And the amount we regularize by is exactly encoded by this learning rate that we've chosen. So this is an equivalent way to write these hedge weights. And another equivalent way is I can just add a constant to this objective. So this is a constant because our weights are actually in the simplex here. And so this term sums to 1. And so you're saying, great, why did you just add a constant to your objective function? Well, it's because we can take this purple term here and the orange term and combine them to observe that hedge is actually has a third equivalent way to write it, which is as this optimization problem where we regularize using the KL divergence. And so it's just KL of the weights to a uniform prior. So this kind of explains why we were talking about a flat prior back here. And this should look familiar if you're used to kind of variational Bayes formulations, because this is exactly what the Gibbs posterior is. So if we think of now taking a step back, just having kind of an abstract parameter space, big theta, then the Gibbs posterior is the, or the posterior distribution is the minimum over all distributions on this theta of the expected loss under the posterior distribution plus a regularization term of the KL between the posterior and the prior. And we can also add in a learning rate. This is often called generalized Bayes. And then the Gibbs posterior can be written according to this exponential update rule where this prior pops out. And we see that if the prior is constant in theta, we have a uniform prior, it just doesn't show up. But we see that the hedge update rule can be written exactly like this Gibbs posterior. So kind of two things to take away from this are that the statistical implications of our work is that we can view this kind of hedge update rule and the algorithms we're using in a Bayesian sense. And also, it's going to be much easier to visualize how we're going to change hedge by viewing it in this variational formulation. And in particular, I'll talk about this more later, but we can look at changing what this regularizer term is here in order to better adapt to whatever setting we actually end up being in. So now that I've described the hedge algorithm, I'm going to describe in a bit more detail how we're actually defining these settings in between stochastic and adversarial so that I can talk about exactly what the performance looks like for any setting in between. So we call our settings time homogeneous convex constraints. So intuition here is that the experts and the environment can collude together, by which I mean at each round, the kind of joint realization of experts, which are the x's here, and data, which are the y's, is going to be sampled from an adversarial conditional distribution. So adversarial in the sense that the environment gets to kind of adversarially choose what the distribution will be that generates it, and conditional on both the data and also what the players have done over the game. So kind of the entire history. That's what Dan was showing with that information flow diagram earlier. So formally, we can think of fixing some convex set of distributions D in the subset of all distributions over expert predictions and data. And then at each round, the joint realization of experts and data are going to be drawn from some element of this D. So the environment gets to choose some element. And this element gets to be chosen using the entire history up to time t. And then the experts and data are sampled from this distribution. So in particular, this distribution gets to be chosen using everything that's happened so far. And so this is where we differ from the Rocklin, Sridharan, and Tiwari use of these kind of constraint settings, is we allow so-called non-oblivious adversaries, which means the adversary gets to make their actions updating over time with how the players themselves have been behaving. So a bit more details. Our setting, we require time homogeneous. So this set D cannot change over time. It's very natural to think of letting this D kind of slowly shift over time. And Rocklin, Sridharan, and Tiwari do allow for this to change over time, but currently we require this D to be fixed. But of course, the distribution within the D, that gets to be changing at each round. We also require our set to be convex. And this you can think of if your set was not convex, so it's some weird shape, then the environment has access to, say, it can pick between two elements within the set. We also just suppose it has access to a coin that it can flip to decide which of these actions it's going to pick. So it has access to all the mixture distributions in between them, and it quickly can convexify its set.
So Blair, can I just ask a quick question? So when you say the X, T, Y, T, the distribution of them can be picked depending on the previous history. Mm-hmm. How's it different from just an adversarial setting? I mean, why don't you put the distribution to be just delta function at the worst sequence?
So because we're restricting the choice has to be from within this D. So if this D is all distributions, then yeah, it's going to be that they're going to pick a deterministic selection. But this D may not contain point masses. So because it has to select a conditional distribution from within the D, it's restricted in how adversarial it can be. So this D is kind of encoding how much freedom the adversary has to kind of fully enforce kind of an adversarial nature on the player.
Mm-hmm. Thanks.
And so that's a great question, because that's kind of my third point here is we should be envisioning that the environment is wanting to maximize the regret of the player with their choice of this distribution, but they can only do so subject to this constraint D. So they are restricted in how much they can kind of maximize the regret of the player. And this is encoding kind of how benign the setting is, how close we are to the stochastic setting versus the adversarial setting. So this kind of is a bit of an abstract notion of what these Ds look like. So I'm going to run through some kind of simple examples to give an idea of how they actually show up. So the first kind of easy case is this stochastic setting. So this is a case where we have I.I.D realizations of data and experts at each round, so independent and identically distributed. We can think of this D as just being a singleton. Basically, the environment has no freedom in what it's going to choose. It has to pick the same distribution every time to sample. At the other end of the spectrum, we have the adversarial setting. So here, this D we allow to be the entire space of distributions on experts and data jointly. And importantly, this does contain the point masses. So this contains the kind of usual deterministic adversary that people often study in online learning. Another setting of interest is the adversarial with an expectation gap. So here we suppose that there's kind of a single expert that is always better in expectation than all the rest, and it's always better by at least some amount delta, but the distributions can be changing over time, as long as when you take expectation under that distribution, the same expert is always better and it's kind of identifiable from the rest in expectation. And so finally, we also have this so-called neighborhood of I.I.D setting. So here, fix your favorite metric on the space of distributions. It really does not matter what this metric looks like. and then pick some reference distribution in this space. And now imagine our D is going to be a neighborhood around this reference distribution mu0. In particular, I'm envisioning kind of a ball around mu0 in our metric of radius r. As r goes to 0 and this ball kind of shrinks to a singleton, we're recovering the stochastic case, so the I.I.D setting with this reference measure. As r tends to infinity, eventually the ball blows up to encompass the entire space of distributions, and so we're kind of recovering that adversarial setting as well. And for r in between these two, we're kind of smoothly transitioning between the stochastic and the adversarial settings. So it gives us a notion of kind of what does it mean to be slightly non-I.I.D. So we have kind of a small neighborhood is somehow a slight relaxation. But while that's kind of nice intuitively, it could still be quite difficult to describe what this D actually looks like for any kind of particular application of interest. So in Rockland, Sridharan, and Tiwari, they define the Minimax regret or kind of get matching upper and lower bounds on it in terms of a Rademacher complexity that depends on what these constraints look like. But for a particular setting, that might be difficult to determine what the actual rates are going to be. And so we take a different perspective, which is that we want to characterize this constraint set D using quantities that satisfy a few key properties. So the first of these properties is we want to simplify this abstract complexity. So we want to be able to visualize what does this constraint look like in some more concrete terms. Second, these quantities should differentiate whether the data is going to be easy to learn or not. And it should do so independently of whatever prediction algorithm the player is going to use, i.e. Data being easy is kind of an inherent property of just the data, not of data algorithm pairs. And this distinction is actually not often made in the literature or is kind of glossed over. And finally, we want our quantities to be rich enough to yield matching lower and upper bounds on regret. It's kind of not so useful if we define something to characterize it that really has no bearing on what the regret looks like. So the first of these quantities that we pick is so-called effective experts. So this is a quantity that we define. And this is going to be just a subset of the total set of experts that the player has access to aggregate over and compete against. And these effective experts are defined to be the ones that can be optimal in expectation under some measure in this set D. So if you think of for any measure in the set D, you can take expectation of all the losses, and some number of the experts are best in that under that measure, and that means those experts are effective experts. And then we just union that over all set measures in our set D. We're usually actually interested in the number of effective experts, which is this N0, and that's just the size of this set. So this is analogous to the fact that in the stochastic with a gap setting, there's a single expert that's best in expectation. So here there would just be a single effective expert. The other quantity that we introduce is the effective stochastic gap. So this is a bit more complicated to describe, but the idea here is we want to say what's the kind of how real or kind of separable are these experts? So how much can we differentiate them in expectation? So if you think of taking any distribution mu in our set D, again, we take expectation of losses, and we have a best expert. And we could compare that best expert to the second best, but we're actually going to compare it to the best that is not effective. So we're kind of seeing how separable is this collection of experts that can be good, the effective experts, and the ones that can be bad, the ineffective experts. And then we want to take the inf over that kind of separability over all distributions in our set D. And this is analogous to the gap in the stochastic setting, which just corresponds to the expected loss difference between the best and the second best expert. Okay, so these quantities probably have not yet sunk in as to what I'm talking about of how I'm characterizing constraints. So I'm going to walk through kind of a simple example to give an idea of how these quantities kind of arise. And so just recalling the definitions of them at the top, this example is going to be, we just have 5 experts, and I'm going to be describing the actual distributions of the losses. So imagine I've kind of smushed together the experts' predictions and the data together jointly and pushed them through a loss function, and I'm just talking about the expected losses now. And I'm saying that this distribution set D can be defined by some abstract parameter alpha that as it varies, it completely determines what the expected losses are of each expert. I'm going to tell you that the effective experts are the odd numbered experts. I'm not telling you why yet, but that will become clear throughout the example. So first, let's visualize what these expected losses look like. On the x-axis here, I just have this alpha parameter ranging. So this corresponds to moving through all the distributions that I have in my set D. On the y-axis, I have the actual expected losses of the expert. And then each of these lines corresponds to a single expert. So you can see this line says, this is the expected loss of, say, expert 5. Now, if I pick some specific value of alpha to consider, this alpha 0, that corresponds to picking a distribution from my set D. And I can realize what the actual expected losses are of each of the experts under this distribution. So I see that the expected loss of expert 1 is right here. Expert 3, 2, 4, 5 intersects somewhere up here. So I see that expert 1 is the best in expectation for this specific distribution. So if I was in the setting where we were in the I.I.D world and only this distribution was allowed to be picked, this distribution with alpha 0, then my stochastic gap would be the difference from the best expert to the second best. And so it would be this amount delta alpha 0 here. But as I've described before, the delta 0 I'm actually interested in is the difference of the best expert and the best that isn't effective. And so I haven't yet told you why experts 1, 3, and 5 are effective. But if you just kind of bear with me and believe that for a second, that means that we actually are looking at the gap between the best expert, and we skip over the expert 3 here because it's effective, and just go to expert 2. So we have a kind of a larger gap that we want to consider here, which is nice because that means that we kind of view them as being more separable than in kind of this I.I.D setting. So how do we identify who these effective experts are in order to know what this effective stochastic gap looks like? Well, first, let me highlight which experts can be optimal in expectation, which is the definition of the effective experts. So for the alphas over here, we see that expert 5 has the minimum expected loss, then it's expert 3, and then it's expert 1. So any of the experts that can be optimal for some distribution, which means that they're highlighted at some point along this alpha spectrum, are going to be effective experts. We see that experts 2 and 4 never get highlighted, which means that they are ineffective. They don't lie in this effective set. And then the effective stochastic gap is just going to be the minimum difference between this kind of expected loss of the best, so this highlighted green line, and these red lines here, because these are the best of the ineffective experts. And this minimum actually ends up occurring at this kind of corner point here between the best expected loss and the best expert that is not effective. So this gap here is going to correspond to the delta 0 that is our effective stochastic gap. So hopefully this makes it a little bit clearer of what these two quantities look like. Now I'm going to go back through those initial examples I described the set D for and talk about what the quantities look like for these sets. So again, we have the stochastic with a gap setting. So here we just have I.I.D realizations from a single distribution. We're saying kind of by definition, we only want a single effective expert. There's one that's best in expectation. This is the definition of what that effective expert is. And the effective stochastic gap is just the expected difference between that expert and the second best. The adversarial setting, where our set D is the space of all distributions, now all of the experts are effective. It's possible to always pick a distribution. In particular, you can pick point masses that make whatever expert you want be the best in expectation. And by convention, our effective stochastic gap is infinite here just because it's the inf over an empty set. There are no effective experts. Or sorry, there are no ineffective experts. And the adversarial with an expectation gap setting. So recall here, we're looking at all measures where some fixed expert is always better in expectation, and it's better by some amount delta, but the distributions can still be changing over time. By design, we're saying there's a single expert that's best in expectation. So we have one effective expert, and we've also chosen its gap to be this delta amount. So that corresponds to the effective stochastic gap because all the other experts are ineffective. And finally, we have the neighborhood of I.I.D setting. So recall here is we have some reference distribution, and we've blown up a ball around it with some radius r. Let's suppose that this reference distribution, all of the experts are kind of separated in their mean, so they aren't the equivalent in expected loss. Then the number of effective experts and the effective stochastic gap will depend on what this radius looks like, so how large or small it gets. And it's going to depend in a bit of a complex way, so I'm going to devote the whole next slide to kind of going through what these look like for the neighborhood of I.I.D setting. So just repeating the setting we're in here, under the reference distribution, the expected losses are separated. And I'm also going to remind you of what I told you the adaptively minimax optimal rate of regret is. So I haven't kind of explained why this is true yet, but I'm just reminding it to you, and now you kind of see where these quantities are showing up. So in the case of a single effective expert, we get constant in t log n over delta 0 here. And once we have more than one effective expert, the rate is root t log n0. So instead of having root t log n, the adversarial rate, we get a log n0 here. So what we're interested in is, as this radius changes, how does n0 grow? And also, how does 1 over delta 0 grow? So first, let's plot how the number of effective experts changes. So on the x-axis here, we have the radius increasing from 0 up to, again, kind of arbitrarily large. And on the y-axis, we have the number of effective experts that corresponds to the set D. So at 0, we're in the stochastic case. There's only one measure, so this is the I.I.D setting, and we've supposed that the experts are separated, so there's a single effective expert. There's one that's best in expectation. As we increase this radius up to some amount here, you can think of this as allowing the expected losses to kind of wiggle in both directions. And so they can be getting closer together, but up to this amount, the first expert still is going to be best in expectation until we allow them to wiggle enough that basically they can swap places. And then there's some distribution where now the second expert can become the best in expectation. And at that point, both of these experts are now effective because there's at least one distribution where they are the best in expectation. Then we can keep increasing our radius until eventually the expected losses can wiggle so much that the first and third experts can swap. And then we're going to have another jump, adding the third expert into the effective experts. So to take away from this, as the radius increases, the number of effective experts is non-decreasing. We can only be adding in more effective experts. And it's going to increase discretely, which means that at these kind of jump points, there's going to be a point where the experts can swap positions in expected loss, and we add a new expert to our effective expert set. So we're also interested in how this inverse stochastic gap is changing. So when we have radius 0, we're again in the stochastic setting, there's some delta. And then as the radius increases, as I said, the expected losses get to wiggle a bit, which means they get to become closer together for some distributions, which corresponds to delta 0 getting smaller. So 1 over delta 0 is blowing up. And then, so we see that it's kind of increasing as delta 0 is going to 0 as we approach this kind of inflection point. And then as we reach this point where the experts can swap positions, we see a jump in the number of effective experts, and also our delta 0 drops back down. So in particular, the inverse effective stochastic gap is increasing in between these N0 jumps, and it's going to reset at each jump. The reason that it's resetting is that once an expert becomes effective, we no longer have to compete against it. So we're only looking at this kind of separability between the best expert and the ones that are not effective. So that's why we see this kind of reset here. So we have a lexicographical order over the number of effective experts and inverse stochastic gap, by which I mean for these sets D, as if they are nested, one has a larger radius, then it's going to be harder to learn. And so that means that N0 and 1 over delta 0 is quantifying the difficulty of learning data. So that was kind of one of our stated goals of what these quantities should do. And finally, I want to emphasize that the regret is not blowing up as delta 0 tends to 0. So based on this statement here, where I've written regret as log n over delta 0, you might be saying, wait a minute, as the experts become kind of less and less identifiable, are we getting infinite regret? And the answer is no. Basically, what it means is that as it gets closer to 0, you just incur adversarial regret for a longer amount of time. It becomes harder to distinguish between the experts, so your algorithm does not get to adapt to them. So I'll kind of talk about this in a little bit more detail in a minute, but I just wanted to alleviate your fears. It's not that regret is ever becoming infinite. It just means that as we approach these inflection points, it becomes harder and harder to distinguish between the good experts and the bad experts. So now I've described in some gory detail what this spectrum of settings is that we've defined in between stochastic and adversarial. And now I want to talk about how the hedge algorithm is going to perform along these spectrum of settings. So first, consider playing the hedge algorithm with a learning rate. Remember, that's what parameterizes how the hedge weights are updated, of the form c over square root of t. So this is often called decreasing hedge. As this kind of t increases, it just means that over rounds, you want to be regularizing less and less compared to the amount that you're trusting your data. And so we have any fixed convex set D, which is describing the constraint set, and hedge doesn't have to know what this set D is in advance. So imagine that this is kind of set separately from the algorithm. We want to be able to adapt to this set D. So we prove that if you take the constant c here to be of the form square root log n, then for any set D, so there's some number of effective experts and effective stochastic gap, in the case where there's a single effective expert, hedge gets the right stochastic regret. So it gets log n over delta 0. It's constant in t. But as soon as you add even more than one effective expert, it has to incur adversarial regret. So it jumps all the way up to square root t log n, which is the worst case minimax optimal regret. So it is not able to kind of adapt at all to the fact that some much smaller subset of the experts are optimal rather than all of the experts kind of having to compete against at once. So you might say, okay, well, this square root log n is maybe too much. We're regularizing too much. Let's take a difference. So some constant that doesn't depend on the number of experts. In this case, there is some adaptation that goes on. So here we see a log n0 popping out. So this means that the dependence on the number of effective experts is kind of being adapted to, but it's being done so outside of the square root. And so I haven't proved this to you yet, but believe me that there is an algorithm that achieves log n0 underneath the square root. And so this is a suboptimal adaptation. We would hope to do better than having this outside of the square root. And it's also slightly suboptimal in the stochastic case. It has to get this log n squared term. And so, of course, we proved matching lower bounds for this hedge performance in these settings. So these are actually the rates that it achieves. So that's kind of showing that hedge cannot adapt to whatever setting it's in, at least cannot adapt optimally. But you might say, well, what's the best it could do? And the best it could do is where it knew in advance which setting it was going to be in. So if someone told you that there was going to be n0 experts, then you can pick your hedge learning rate to be square root log n0 instead of root log n. And then you can achieve the right adaptation or dependence on log n0, so it's under the square root now. And for this, in order to not have a 0 learning rate, we need the number of effective experts to be larger than 1. And so this term is essentially kind of lower order because we always are going to have a square root t dependence here. But this is nice, but it's not so nice because we don't want to have to know in advance which setting we're in. So this is not satisfying kind of adaptive minimax optimality where the same algorithm has to work regardless of what setting it's in. What this does, though, is tell us kind of what are the fundamental limits of performance if you did know the setting in advance. So all of these regret bounds I've stated have terms involving a t. So what this t corresponds to is after some amount of time, the algorithm is going to adapt or maybe not adapt to the setting, but try and adapt. And then it's going to incur regret kind of growing in this long run sense. And so that's what these square root t terms are corresponding to. And then there's also these extra terms which have this delta 0 and n dependence. And this is basically how long the adaptation period will last. And so again, as I said, this does not correspond to kind of regret blowing up to be infinite. What it just means is that as delta 0 goes to 0, it becomes essentially impossible for the algorithm to distinguish between the two experts. And so it has to spend infinite amount of time incurring adversarial regret. And so it just never is able to adapt to the setting. And so it's not infinite regret, it's just it achieves that worst case root t log n if this delta 0 kind of shrinks down to 0. So this is kind of the state of the world for hedge. And now we can ask, can we do better than this? So without knowing n0 in advance, can we match this dependence that hedge achieves, wherein hedge is told what n0 is in advance, while also matching the stochastic case dependence on log n and delta 0? And we don't have to know in advance anything about what this constraint set is going to look like. Well, the reason we're giving this talk is because the answer is yes. And we introduced 2 new algorithms to do this. So the first of these algorithms is kind of the workhorse, and then the second is just going to modify it a bit in order to make sure it's optimal everywhere. So the first we call FTRL care, which I'll explain in a minute. And what this does is it achieves the optimal dependence on n0, and it does so without having to know which setting it's living in. So it does so across the spectrum of stochastic and adversarial. But in the stochastic setting, it has a slightly worse dependence on log n. So it's still constant in t, it's just not exactly log n over delta 0. And so we would hope to kind of alleviate that in order to be truly adaptively minimax optimal. And to do so, we introduce metacare, which says take the kind of best parts of FTRL care, which is in all of these spectrums outside of I.I.D, and then use that hedge is optimal in the stochastic case and kind of take that best part to merge them together and achieve all 3 of these desiderata at once. So optimal dependence with no knowledge about which setting you're going to be in. So now let me describe what these improved algorithms actually look like. So to give some insight on how we're going to modify hedge to get an optimal algorithm, the first thing is that from the oracle hedge bound, so when hedge knew in advance what n0 was, we saw that the learning rate to pick is square root log n0 over t. So we would hope to be able to pick something like that without knowing in advance what n0 is. Also, I haven't told you this, but it might be kind of intuitive from the fact of how hedge is defined with respect to the Shannon entropy, is that the regret depends closely on what the Shannon entropy of the weights is over time. And in the worst case, an adversary is going to force these weights to concentrate to a uniform distribution over the set of effective experts. So this subset of experts that can be good. And so based on what the entropy of a uniform is, we're going to see that that corresponds to log n0. And so if we could somehow pick our learning rate to just be square root of entropy over time, then once this entropy starts looking like log n0, our learning rate starts looking like exactly what we would hope it is from that kind of oracle hedge bound. The problem here is that now our learning rate depends on the weights at time t, but the weights at time t are defined using the learning rate. So we have an implicit equation. So we have to set up how can we actually formally achieve this. The way we're going to do so is using the follow the regularized leader framework. So this is kind of a generic class of algorithms that are fundamental in online linear optimization. And they are going to be parameterized by some sequence of regularizers, so mapping weights to just a real number. And they look familiar to the variational form we gave of Hedge, which is they solve an optimization problem. So the weights at time t plus 1 are the minimum of weights in the simplex, so actual distributions on experts of this linear term, so expected loss, plus just a regularization term of the weights. So Hedge corresponds to taking this regularizer to be the negative Shannon entropy over the learning rate. And now, because we also know the explicit update rule for Hedge, being this kind of exponential update rule renormalized by the finite number of experts, we can say that the solution to this optimization problem is exactly defined by this. And so now we're going to say, how can we kind of use FTRL in order to improve on the Hedge algorithm? And we're going to do that using our new algorithm, which is FTRL care. So this is follow the regularized leader with a new regularizer that we call the constraint adaptive root-entropic regularizer. So constraint adaptive because we want to adapt to whatever setting we live between stochastic and adversarial without having to know in advance what that is. And root-entropic because Hedge regularizes by just the entropy, and we're going to regularize by square root of entropy here, where this term is still just the learning rate showing up. And so you see that this is still just the follow the regularized leader equation, but where we've picked a specific regularizer, and we prove that this actually ends up solving this system of equations. So where we have the weights equal to a normalized exponential update rule, but this is now an implicit update rule because the learning rate depends on the entropy of the weights over time. So this is exactly the kind of setup that we wanted to be satisfied for the learning rate in order to get something that looked like that Oracle hedge bound. And indeed, we're able to use this to prove that for any set D, so FTRL care doesn't have to know what that set is, it's able to achieve the right dependence on N0. So it gets root T log N0 dependence for the number of effective experts. And it almost gets the right thing in the stochastic case. So it has the constant in T. When N0 is equal to 1, this is just 0. And so it's only paying for this term, which is constant in T, but it has log N to the 3/2. So if that 3/2 was a 1, we would be done. But it's not, so we have to do a little bit more to get adaptively minimax optimal. And for that, we're going to use metacare. So again, the idea is FTRL care has the optimal dependence on the number of effective experts. But in the single effective expert case, it has a slightly worse dependence on N. And so we want to combine FTRL care with the Hedge algorithm, which does do optimal for the case of the single effective expert. And we're going to do this using metacare, which says have kind of two instances running, one of Hedge and one of FTRL care, and treat their predictions as basically meta experts. And then aggregate over those using one more instance of Hedge. And we're going to incur the best regret of the two, so whichever one does better, whether it's in the stochastic case or more than one effective expert, plus some additional amount that we have to incur from doing this kind of meta learning over these meta experts. And the point is we can prove that this additional amount of regret is kind of negligible. It's not affecting the overall order of the bound. And so metacare basically achieves the best of both worlds here. It gets the right dependence on N0 that it recovers from FTRL. In the single effective expert case, it gets this right dependence from Hedge, so just log N over delta 0. And then when there's more than one effective expert, it gets this dependence from FTRL care, so it has a log N to the 3/2. But in this case, the root T log N 0 term is going to be dominating. So this is basically a lower order term that doesn't affect whether it's adaptively minimax optimal. And so what this means is metacare actually achieves the minimax optimal rate across all spectrums, stochastic to adversarial inclusive. Okay, so let me kind of summarize all of these results I've discussed here. So first, we introduced a spectrum of relaxations to the I.I.D assumption. And we do this using time homogeneous convex constraints. So these sets D, which the adversary has to pick their distributions from within. And we want these constraints to interpolate between the very stochastic setting to the full adversarial case, because we don't believe that our data is going to be kind of either exactly stochastic. It's too pessimistic to think of it as adversarial. So it's going to be somewhere in between, but we don't want to have to know where it is in between. And so we want to be able to do optimally well, regardless of where it shows up. And then we characterize the difficulty of learning data along this spectrum using two quantities, this number of effective experts, N0, and the effective stochastic gap, delta 0. And so these characterize what these constraints look like. And then we defined what it means to be adaptively minimax optimal. So what does it mean to perform well in kind of all settings simultaneously without having to know in advance which setting you're going to be in? We derived regret bounds for hedge along this entire spectrum and showed that there's dependence on n0 and delta 0, but if it doesn't have knowledge of what n0 is in advance, it can't achieve the adaptively minimax optimal rate. So it has to know in advance which setting it's going to be in, which means that it's not adaptively minimax optimal. And then we provide a new algorithm, Medicare, which builds on our new modification of FTRL, which is FTRL care, and regret bounds for it that adapt optimally to the full spectrum of settings between stochastic and adversarial. And the point is it adapts optimally without having to know in advance what n0 is or delta 0 is or anything about these constraints. OK, thanks. I think we have time for questions now, hopefully.
Thank you very much. Any questions?